Hi guys. The other day we calculated how much current we could get out of putting some resistors in series, which is to say one after the other. And I just thought we'll complete that discussion by talking about what happens if we put these resistors not in series, not one after the other, but actually in parallel. So the idea here being that a bit of current comes out of our battery, out of our cell, makes its way around the circuit, but when it gets to this point here, it actually splits in two. So we end up with two different currents going through each of our resistors. So I'm just going to show you how to do the calculation there to work out what I1 and I2 are, and ultimately what this I here is. Now remember, current is about counting charges going past. So I1 plus I2 better be equal to I. So let's start by putting that on the page. So at every junction where our current might split, it's going to be the case that the total amount of current going into that junction, so I going into this junction, has to be equal to the total amount of current coming out of that junction. So let's make that a really clear rule here. At every junction, the total amount of current coming in equals the total amount of current coming out. So that's going to be one of the rules we're going to use when we're talking about parallel circuits. The other rule we're going to use is to do with voltage, and in order to understand that, we might put some numbers on this. So let's say we put, let's say 12 volts on here, and let's say we make these resistors 10 ohms and 25 ohms. Just putting some numbers. So first off, just before we even begin, what should we generally expect? We should generally expect to get more current down this arm here than this one here. So I2 should be bigger than I1 because I2 faces less resistance, so we'd expect more current. Okay, what else can we draw out of this? Remember that voltage is a resource. So potential energy is a resource that gets consumed as you move your way through the current, and it gets consumed in the elements of that circuit. So not in the wires, but in the resistors and other components that we'll eventually get to talking about. So that means as the charge moves through the circuit, when it gets to this point here, it still has 12 volts. And when it gets to this point here, because that's joined with a wire to the 0 volt position, it has 0 volts. So what we can see here is that regardless of whether the charge takes this path around the outside and goes from 12 volts to 0 volts, or takes this path straight across here, it goes from 12 volts to 0 volts. So either way, the same total amount of energy is used up per charge on either of these paths. And that's actually the other rule we apply for resistors in parallel, is that V1 is actually going to equal V2, where these two things are measured across this resistor. Let's call that V1 to go with I1, and or across this one here. Alright, so the total amount of voltage, that's energy per charge, getting dropped on this resistor has to be equal to this one, because either way you have to lose that 12 volts somewhere, and each charge is either going through this one or going through this one, so it must lose that 12 volts in there. Okay, so our second rule for parallel circuits is that the potential drop getting from point A to point B has to be the same no matter what path you take, because the potential is a property of this place in the circuit, and the 0 volts is a property of this place in the circuit. So it doesn't matter how you get from this place to this place, you have to lose that 12 volts somewhere in between. And if there's only one resistor on each path, then that makes it easy. That means there must be 12 volts getting dropped across this resistor, and there must be 12 volts getting dropped across this resistor. Okay, at this point we can start using Ohm's law. In particular, we know the resistance of R1, we know what voltage is getting dropped across it because we know it has to be 12 volts. So we're going to be able to find that current there, and then we're going to be able to do the same thing for I2. So let's do that now. So I1, the current through number 1. So this would be if we placed an ammeter, let's say here. The current that that ammeter there would read would be the voltage across that resistor V1, so that's 12 volts, divided by the resistance, 25 ohms. So the more voltage you have, the more current. The more resistance you have, the less current. And that's going to be equal to 0.48 amps. Okay, let's quickly do the same thing for I2. So now we've only got 10 ohms resistance, but the same voltage. So 12 volts over 10 ohms equals 1.2 amps. And so finally we can say the total amount of current that this circuit draws is 1.68 amps. So that would be if we put our ammeter here or here, either before they've split up or after they've recombined. We would get 1.68 amps. Now, the last question we could ask is, what is the effective resistance of these two here? So basically asking the question, if we put 12 volts on this circuit and we get 1.68 amps out, well, we could use Ohm's law on the total voltage and the total current to get a sort of effective resistance for these two resistors combined in this particular way. And that's a general skill we're going to use a lot in when we're talking about electrical circuits, is to sort of bundle different resistors together and give them an effective value. So let's look at, if we just apply Ohm's law to this, so apply Ohm's law total circuit, we get V equals IR leads to 12 volts equals 1.68 amps times some RT, T for total, and we get RT equals 7.14 ohms. Now, the really important thing to get your head around here is that this 7.14 ohms is smaller than either of these resistances on their own. So by providing the charge with an alternative path, you're actually lowering the resistance. It's like saying, so imagine starting with just this 10 ohm resistor in here and not having the 25 ohm, then all of this charge that starts with 12 volts faces a 10 ohm barrier, we would get 1.2 amps of current. Then by adding a separate path on here, well, we can only add more current because we already had 1.2 amps flowing. By adding an alternative path, we're not going to drop the amount of current. We're only going to maybe add a little bit more. So the effective resistance of two resistors in parallel is always actually going to be less than the resistors on their own, any one of the resistors on their own. And that leads us to the last the third general rule for parallel circuits. So let's write it down here. Total resistance of multiple resistors in parallel is always actually less than any one resistor alone. And that's obviously opposite to the case with a series circuit where each electron has to pass through multiple resistors, and so the resistance there is adding up. In this case, the electron has a choice between going this resistor or this resistor, which means we get more total current, so the effective resistance is actually less.